Hello everyone, welcome to this week's lecture. We're talking about multiple linear regression. This builds off of what we talked about last week with simple linear regression. In simple linear regression, we had a response variable that was a quantitative variable, and we had an explanatory variable that was also a quantitative variable. With multiple linear regression, we're going to talk about the situation where we have more than one explanatory variable, and we can even consider some explanatory variables that are not quantitative, that are categorical. Let's dive right in. Quick outline, the readings for this week. You have the chapter from Gersman, but then you also have some supplementary material. You have the links available to you to download as PDFs. These are all books that are available for free via GWU. You have a chapter from Bobko, a chapter from Pace, a chapter from Dalgard. Dalgard and Pace are really good because they use R and they talk about a lot of the important concepts that we're going to be talking about. But multiple linear regression as opposed to simple linear regression is quite difficult to calculate by hand. So we're not even going to go over that. So if you're doing multiple linear regression, you need to know how to interpret statistical output from a software package. So Pace and Dalgard both review that, specifically with R. R is what I'm going to be using in my example today. R is really common in academia. In public health, you see a lot of STATA and SPSS. Sometimes you see SAS in the more biostatistical communities. Uh, Dalgard is really just applied, but Pace does a good job of explaining the concepts underlying multiple integration as well. Bobko doesn't include any R output at all. He just focuses on describing some important issues such as collinearity, etc., that supplement the chapter from Gershman. So we'll talk about all of these things, all of these issues that are related to multiple linear regression, and we'll do an example. It's actually not from the book, but we'll do an example nonetheless, and then we'll talk about this week's assignments. So multiple linear regression, just like simple linear regression, the first thing to remember is that it is a model. Therefore, it is one, an abstraction from reality, and it also assumes and forces a structure onto a data. This is really problematic. I found that most of the time, most data sets do not actually have a linear structure. So I am not a huge fan of multiple linear regression. I think it's an important tool. I think that the generalized linear regression, which I'll talk about in a little bit, which is very similar to this, is important. So multiple linear regression is a very important concept to learn. But I'm also a big fan of some of the newer age data mining and data algorithmic modeling procedures. But that being said, please do remember that you are assuming and forcing a structure on your data. Now, if you know that your data has this structure, then multiple linear regression is perfect. You absolutely should be doing this. The basic model, again, is where you have one explanatory variable and one responsive variable. That was simple linear regression. So our basic multiple linear regression is we have more than one explanatory variable and still one response variable. So as opposed to a response equals an intercept plus a slope times an explanatory variable. Now we have two different slopes and two different explanatory variables. And they're not really quite slopes anymore because we are not just talking about straight lines. With two explanatory variables, we're actually talking about a plane. That's what Gersman talks about. He's got an example of this and a picture of this. But really, it's the idea that each slope or each regression coefficient for each of the explanatory variables helps to quantify the incremental increase in the response variable based on changes in the explanatory variable. So let's say our explanatory variable changes by 1. Well, then our slope, or slope number 1, will tell us how much the response variable will increase by. And so that's how you interpret all the slopes. And we'll do an example of this as well. In statistical notation or mathematical notation, again, we still use betas for the regression coefficients for the slopes, alpha for the intercept. We still have the error term. Those error terms still need to be normally distributed. And now we have just multiple explanatory variables. Our method is the same. Our method is still least squares. And again, least squares regression is all about identifying the regression coefficients that minimize the sum of the squared residuals. The residuals, again, being the observed response variable values minus our predicted response variable values based on our model. There's an extra assumption here, though, that the explanatory variables are mutually independent. This is really important. This assumption is needed in order to be able to solve the least squares regression problem. And this is not always the case. There's a really good strategy that can be used to avoid mutually independence. I'll talk about that in a little bit, but it's not used because it makes interpretation difficult. But this linear dependency is called multicollinearity. Basically, we don't want the explanatory variables to be strongly correlated to each other. It's going to kind of throw off the effect of the model. It's going to throw off the calculation of the regression coefficients. It's going to throw off the t-tests for each of the slopes, each of the regression coefficients as well. So it's better if, or really ideally, none of the explanatory variables are related to each other. So we'll assess this with correlation. You guys all know how to do that. And if variables are strongly correlated, we'll talk about how to handle that in a minute. There's still the same normality assumption here, and you guys should be pretty good at assessing normality by this point, so I won't spend too much time. Just to note that residual versus predicted plots plus residual versus the explanatory variable plots is really important. So residual versus predicted, residual versus observed, or residual versus explanatory variables. There's many ways that you can take a look at the residuals. That's going to give you a better picture and will help you assess whether or not these residuals are actually following this normal distribution with mean zero and unknown but constant variance. So we said simple linear regression, we said multiple linear regression. What does linear actually mean? Now, I referred to this last week when I was talking about simple linear regression. Now, simple linear regression, we're talking about straight lines. So the data needs to have a straight line pattern. Gersman, and a lot of people do this, they call that a linear pattern. I think that's incredibly confusing because what we mean by linear when we say linear regression doesn't actually mean straight line. It means something totally different. It's in reference to the regression parameters. The regression parameters all have to be separate from each other, basically. So if we look at these examples of a linear model, the regression coefficients are all separate. They're all linear combinations of each other. And this linear combination is a term from matrix algebra, also called linear algebra. And basically, they're separated by addition signs, right? Whereas if we take an example of nonlinear models, the regression coefficients are not, they're quite different, right? So here in the second one, we've got one regression coefficient here that's being raised to a power that's the explanatory variable, then that's going to be divided by the explanatory variable plus another regression coefficient. So this is not a linear relationship. They're being like divided by each other. Same thing here. One of these regression coefficients is actually the exponent where the explanatory variable is the base. That's not linear either. Linear is something like this, where the regression coefficients are being multiplied by something, but then are all just kind of being added together. So this is what linear is. And note that the explanatory variables, we can perform transformations on them. So even though it's alpha plus beta 1 times x1 squared, this is still a linear model. This is still okay. Because again, linear is not talking about what's happening with our explanatory variables. It's talking about what's happening with our regression coefficients. And our regression coefficient is fine. I think if you remember that what the equation of a straight line looks like, the y equals mx plus b, our linear model needs to look like that. So here's y equals, here's our m, m1, m2, m3, those are our betas, those are regression coefficients. And then here's our intercept. And then we always have an error term. So these are both linear models. And again, we've got transformations here. So x1 squared, square root of x2, the natural log of the quotient of x1 by x2, and then even the sine of x1 raised to the x2 power. That's all okay. And we can generalize this to be any function on our explanatory variables. Now, these two terms, where I'm taking the log of the quotient and the sine of one variable raised to the other, are called interaction terms. And they're generalized to this, where I've got a multivariable function. Interaction terms basically means that a variable might interact with one another. I suppose that was somewhat self-evident, but it's that they have an effect on each other that we need to be able to capture in our model. So an example of this would be if we're trying to create a model for temperature and we're using for a specific city, and we're trying to figure out how to predict temperature based on time of day and what day it is in the year. Well, these two variables interact with each other because if we think about how warm it is on average, let's just use the city of Houston, who just won the World Series, 7 a.m. on January the 1st. The temperature on January 1st at 7 a.m., first of all, is going to be probably different than the temperature at 3 p.m., right? But it's going to be very different than the temperature at 7 a.m. on a different day. On January 1st at 7 a.m., it's probably going to be much colder than on 7 a.m. June 1st. So there's an interaction here. Not only do we need to know the day of the year, but we also need to know the time of day, and what time of day is combined with day of year is really important. For example, in January 1st, maybe at 7 a.m., it's only 5 degrees colder than what it's going to be by noon. But on June, it's going to get really cold overnight, but then it's going to really heat up. So maybe by noon is going to be 15 degrees warmer by 12 p.m. So this is an interaction, and our model needs to include this interaction. So as opposed to just being, beta 1 times x1 plus beta 2 times x2, we need to have one of these plus beta 3 times x1 times x2 terms. And that's what we saw here. These are interaction terms where we're combining our two explanatory variables, or we're combining explanatory variables, and we're adding them as a separate term in our model. Okay. So I also briefly mentioned collinearity. This is when our variables are related to each other, and our explanatory variables need to be independent. The easiest way to assess this is by a correlation matrix. A correlation matrix, or scatter plot matrix, basically just calculates the correlation coefficient that you saw last week for all possible combinations of all of our quantitative variables. So that's a really quick way. If we see patterns then this is a sign that maybe this isn't so good. So the strategy that I really like to do is called principal component analysis. Principal component analysis, very similar to factor analysis. It's actually the same thing as factor analysis, but the term factor analysis tends to get used in public health and the social sciences a lot more. It's also related to the idea of eigenvectors, if you're familiar with those. But the idea is that we're taking our explanatory variables and we're going to transform them onto a set of or a space that has independent factors. So we basically are going to take our data and put them somewhere where the number of variables that we're going to describe them with are all independent by definition. So that totally would satisfy our problem or assumption here that our explanatory variables are independent. So how come we don't just always do principal component analysis? Well, it's because it's quite difficult to interpret. And so people tend not to do it. So you see a lot of principal component analysis when people aren't interested in the interpretation of a model. If a model is just kind of a black box and they just need to be as accurate as possible, then they'll do principal component analysis. But if you need to describe the model and people need to understand the model and develop an intuitive sense, it's quite difficult to do that when you've done a principal component analysis because everything kind of gets mixed up. But please be aware of collinearity. Again, we're going to examine it with a correlation matrix, and there are avenues available to you to solve the problem if it exists, but we're not going to focus too much on that. I just want you to know that solutions do exist. Okay. In simple linear regression, we had a rule that the explanatory variables had to be quantitative. That's not actually true. We just kind of made that up for you. Now, ANOVA actually is the same thing as simple linear regression if your explanatory variable is categorical. So I'm not going to go into this too much, but I've shown here that if we have a model with just one explanatory variable that's categorical here, let's just call it sex, so we have men and women, we can write a model in the form of a linear equation that is essentially the same thing as an ANOVA. You have two different group means, and your slope or your intercept is going to change based on which group you're talking about. And if you get a statistically significant result, then that means that your two groups have different means. And that's exactly what ANOVA was. And we can do this with any number of indicators or any categorical values with any number of levels. Now, that being said, it's inefficient. It's much better to do an ANOVA, because in ANOVA we can just have our factors, and we the output that we get is quite easy to interpret. In simple linear regression, we have to combine or we have to flatten our categorical variables into indicators that only compare two variables at a time. So Gerstmann talks about doing this. I generally don't like doing this, and will try to avoid it when possible. That being said, it's a quite powerful tool and is quite common. And towards the bottom of the slide, I have an example of a situation where we have one categorical variable as well as one quantitative variable. And again, it basically reduces the problem to doing a separate regression of just the quantitative variables within each group of our quantitative variables. But that's only if we think that these groups are actually different. But we can handle categorical variables. They just need to be transformed into dummy variables that either equal 1 or 0 for the different levels of our categories. Okay. We also oftentimes have several variables. So maybe we have one response variable and we collected data. We weren't sure what was going to be a significant predictor or significantly related to our response variable. So we have data on 5 other variables, but maybe not all 5 variables belong in a model. So there's something called model selection. There's several different ways to go about doing this, but the idea is that sometimes too much information is a bad thing, and too complicated models is also a bad thing. So we strive for this notion of, it's related to the idea of mathematical elegance, but the idea that the simplest solution is best. So we try to balance the predictive power of a model against its simplicity. And the term a parsimonious model is what's commonly used. A parsimonious model is a model that successfully balances the number of explanatory variables that you have against the amount of information that is explained. So let's say we have a model that has 3 explanatory variables that explain, 99% or even just 90% of the variation. If we add a 4th explanatory variable, and that explains an extra 0.5% of the variation, is that really worth it? Is that extra 0.5% really worth another variable? Is that variable really important? And the answer that you'll find most statisticians saying is no, it actually isn't. It's not a significant predictor. Now, that doesn't mean that it isn't important and doesn't play a role, but there's this idea, again, of parsimonious models. The simpler the model, the better. We try to isolate the major effects, and if once we've captured about 90 or 95% of the variation, unless there are factors that are still contributing large amounts of explained variation, then we tend to stop including them in the model. Because we also want to be wary of overfitting. Overfitting is where we have some data, but perhaps our sample size aren't large enough, and so we have random error terms, but we interpret these random errors as actual patterns and model these patterns that are actually not a thing. So this is related to type 2 error rate, or type 1 error rate. But our type 2 error rate is essentially overfitting. So we don't want to overfit. So we try to strike a balance between this. Now, we're not really going into how to do this with model selection. I do want to expose you again that there is a thing that you don't always include all the variables. In fact, very rarely are you going to include all the variables that you have data for. That's almost never done. Gerstmann doesn't really talk about this. Some of the other readings do mention the different selection procedures. I think stepwise selection is probably the most common procedure. And so there's forward selection, backward selection, and stepwise. With forward selection, you start with a model that only has an intercept, and then you slowly add in predictors. With backward selection, it's you start with a model that is called a full model that has all of the possible predictors, all of the explanatory variables, maybe even all of the interaction terms. And then you remove some one by one until you get a model that you think is best. Stepwise is you can start really anywhere. Usually you start with a full model, and then you do both forward and backwards at the same time. So you'll ask at every single step of the way, does eliminating any variables help, or does adding any variables that have already eliminated help? So I think it's the best. I think it's better than forward or backward selection. There's different selection criteria that are important, but again, we're not going to go into that at all. Just again, note that we don't always include all of the variables that we have into our models. And remember, again, that correlation is not causation. And this is related to the idea of overfitting. We don't want to overfit. And so we will try to stick to just finding and isolating the variables that are significant predictors. Okay, I'm going to do an example in R, but first I want to introduce you to some R outputs. So this is just a random data set that's part of R. Over on the right, we see this scatter plot matrix. So this is what we might use to assess collinearity. And the way that you do that is you're looking for patterns in each of these scatter plots. So for example, here when we're comparing the gravity variable against pH, I don't really see a strong linear pattern. But when I look at gravity against this osmosis variable, there's a very strong linear pattern. So this, to me, says that gravity and this osmosis variable are very strongly correlated. That's not good. Same thing here. There's still a linear pattern. It's not quite as strong. There's a strong linear pattern here with gravity and urea. And maybe you could argue that there's a linear pattern here between gravity and calcium, but I don't think so. Similarly, again, with osmosis and this condition variable, there's a very strong linear pattern. With osmosis and urea levels, there's another very strong pattern. So when we assess these, we need to make sure that we're doing something about it. And we can best handle this if we want to still include the information from all the variables. I like principal component analysis. We're not going to do that. For this class, what you need to know is, hey, this is a problem. We should either include an interaction term or we should consider dropping one of these variables because it's so strongly correlated. And the idea is it's if we have our and let's say we're including osmosis as a significant predictor of a response variable, which is calcium. Because osmosis and this condition variable are so strongly correlated, they're basically the same, right? So we'd be counting that same information twice. We don't really need both of those variables in our model. We only need one because they're so strongly correlated. So if we factor in osmosis, we don't actually need the condition variable. When we go and look at the R output, and we did this a little bit last week, but we have multiple coefficients, which are the regression coefficients for each of the different variables that we put into the model. We have the estimates for the coefficients. We have a t-test for this coefficient. We have p-values. But if we look at the p-values, none of them are significant. Why is that? Even though the model is highly significant, none of the predictors are significant. Well, that's because of this issue of multicollinearity. When we have multicollinearity, it really screws up with the p-values because each of these variables is trying to be assessed independently, but they're related to other variables. So when the other variables are present, these variables don't actually add anything, so none of them are actually significant. But if we remove one, that might change the significance level of the other variables. So if we submit this full model to a stepwise selection procedure, the procedure tells us that the model that we should stick with is calcium plus the condition plus the osmosis. But we just said osmosis and condition are highly correlated to each other, yet they're both significant in a model. What's going on here? Well, again, This is why humans still need to be in control of computers a little bit. It's because of the nature and the procedure that is utilized with stepwise regression. This is not a good model. We should definitely not run with a model that has calcium being predicted by osmosis and this condition. We really only need one of these variables, and perhaps there's an interaction that's being hidden somewhere here. But we will need to do some other analysis. And that other analysis is residual analysis. But just to review again with our output, you should know how to look at a scatter plot. So the scatter plot matrix is just a lot of scatter plots all in one go. And then we have these tables that is the output whenever we do a regression. You should know how to pull out the regression coefficients, the estimates, and then the p-values. So let's practice interpreting one of the regression coefficients here in this second model. So the intercept says is 0.147. What does that mean? It means when the osmosis variable is equal to 0 and the condition variable is equal to 0, our expected calcium level is going to be equal to 0.1472. Now, for every increase in one of the condition variable, we expect the calcium levels to decrease by 0.116. So again, our regression coefficients, or the estimate of our regression coefficients, correspond to the incremental increase or decrease in our response variable based on the explanatory variable. Similarly, if the osmosis variable increases by 1, we would expect our calcium levels to also increase by 0.01. Okay, so hopefully you don't have any questions there. Again, we have t-tests here, and each of these t values, the test statistics and the p-values associated with them, are for the regression coefficients. So 90% test for the regression coefficient of this condition variable would say that it's not significant, and that osmosis is highly significant. Because they're both so strongly correlated with each other, I would actually drop this condition variable completely and just keep the osmosis variable. But that is how we interpret this R table. Again, both PACE and Dalgard have more examples of interpreting this, so definitely read those assigned readings. Very quickly, I want to just, again, put in front of you the proposed general statistical procedure. Do exploratory data analysis and then formulate a hypothesis. Figure out what test you want to do and make sure that it's appropriate to use that test. Here's the 10-step hypothesis test procedure that you need whenever you're doing hypothesis tests. This doesn't really apply to regression per se, but for testing correlation or the significance levels of any of our regression coefficients, we would need to follow this because those are both t-tests. And our multiple linear regression procedure, which is very similar to our simple linear regression procedure. Again, we're going to do exploratory data analysis, which is scatter plots. If we have categorical variables, we're going to do box plots. We need to assess normality, so we'll do that with QQ plots. We need to also assess the assumption of mutual independence or collinearity. We'll do that with the scatter plot matrix. If we suspect possible significant correlations, we need to do a t-test for statistically significant correlations. So we know how to do that, the t-test for R. Then we're going to assess the assumption of the straight line relationship or the multiple linear structure on our data. Then we'll calculate our regression coefficients, maybe do some model selection, and then we need to do some regression diagnostics. We need to examine residual plots. We'll do an example of this, and I'll talk a little bit more about how to do that when we get to the example. Then we should also always consider transformations of explanatory variables and interaction terms. Now, this is usually only done unless we have strong evidence in our exploratory data analysis of patterns in our explanatory variables or interaction terms. This is usually done to control residuals. If we see some patterns in our residual analysis, that's not good. That means that the data doesn't actually fit our structure. So then we might transform explanatory variables, add in interaction terms, maybe try to manipulate the structure of the model to better fit the data. Because again, the assumption is that the residuals or the errors are normally distributed with mean zero and constant variance. So if they're not, that's a sign that the data do not have the structure that the model is forcing onto it. And that's really important. So paying attention to residual analysis is key. Once we have done that, then we want to perform an ANOVA to see if we have a statistically significant model. And I'll go back and we'll talk about that R output again. We basically are getting the results of an ANOVA. That's what this F test is, the F test statistic. Again, it's not really presenting that ANOVA table to us, but last week we talked about how we could calculate that ANOVA table for the residual sum of squares and the regression sum of squares. So ANOVA is at the heart of this procedure. Okay, and once we've done that, then we also want to perform t-tests to see, identify statistically significant explanatory variables. Okay, so we're going to do an example. It is fictitious. I'm going to do this in R. I have some data on the wages of certified nurse assistants. And we think that maybe there might be some differences in wages based on whether or not you're male or female. We think there's been a history of some gender bias in this department. So it's supposedly gotten better, especially with doctors, but we want to make sure that it's going all the way down and that CNAs are also getting paid fairly. So we have data on the hourly wages of several CNAs employed by one hospital department. We know what gender they are. So sex num is just, I've transformed this into a quantitative variable. So again, this is in anticipation of doing a multiple linear regression model where I need to create a dummy variable. So here sex num equal to 1 is for men, sex num equal to 0 is female. So female in a sense is going to be my base, and I'll add a term in to see if the group average for males or the slope for males is any different. And then I have the number of months that they've been working at the hospital. So usually CNAs don't stay at this hospital very long. Most of the CNAs tend to be college students or students, wanting to apply to med school or wanting to apply to nursing school or maybe even apply to get paramedics. So it's kind of like an entry-level position at this hospital. So we have the number of months that they're working for. And we think that we want to do a multiple linear regression, but before that, let's do some exploratory data analysis. So the first thing is, let's see if salary and months are correlated to each other. And indeed they are. They're quite strongly correlated to each other, 0.6917. So that's quite strong. I think salaries, or the number of months that people are working, is probably a strong predictor of salary. What about salary by sex? Well, looking at the box plot, it looks like maybe men make a little bit more, but there's a lot of overlap between these box plots. So maybe this could actually be explained by how many months everybody's been working. Because maybe if men have been working there a little bit longer, you get raises every, maybe 3 months or 6 months. That might explain this. So let's take a look at that. And this is the work experience number of months by sex. And it looks like men and women, pretty much the distributions are the same. So if men and women have more or less worked the same, then their salary should be the same too. But men had slightly higher salary. So now I'm starting to think that maybe there is still some gender bias here. And just to make sure that that sex and the number of months, the work experience, are not related to each other, because these are both going to be explanatory variables, I'm going to do a t-test, a 2-sample t-test, because I don't have 2 quantitative variables. Here, sex is a categorical variable, and I have the quantitative variable as months of experience. So the way that I identify relationship here is with the 2-sample t-test. So let's run that, and the output that we get is we get a p-value of 0.8. That's quite high. So there is not statistically sufficient evidence to suggest that the number of months of work experience for CNAs at this hospital differs by sex. The sample mean for men on average have worked 11.5 months and women 12 months. So that's quite close, and there's, again, a lot of overlap. So the t-test corroborates what we saw with the box plots. But let's take a look at the effect of experience on salary. And for men, it's quite strongly related. It's even more strongly related than overall. The correlation coefficient is 0.846. The correlation coefficient overall for the relationship between experience and salary was 0.69. And let's do the same thing for women. For women, it's a little bit lower than that of men, but it's still quite strongly correlated at 0.6828. So what's causing this different correlation? Well, again, I think that as we saw with the box plots, the side-by-side block plot, that men seem to make more. So if men are getting more, then once we isolate that factor, the relationship between experience and salary is more accurately explained. We're controlling for some of the variance now because we've limited to the specific genders. It's interesting, though, that there is not a similar increase in the correlation coefficient uh, in women between experience and salary. So we'll have to take a further look at that. And just because visualizations are always nice, here's a scatter plot of months, so experience by salary. And I have different colored dots here for the men and the women. And let me try to maximize this as much as possible. Whoop, that's not what I wanted. Here we go. Okay, so the red dots are the women, the blue dots are the male, and the males looks like for those that have more than 10 months of experience, the blue dots all appear to be higher than the red dots. So it looks like after about 10 months or after about the first year that men do seem to make more than women. Before that, the blue dots and the red dots are kind of all pretty low. They're all kind of between this 10 and 11 range. So that looks like if there is a pattern, it's only for those who have worked a year or more. So actually, yeah, about, well, at least more than 10 months. So on this left half of the graph, there doesn't appear to be a pattern. On the right half of the graph, there does appear to be a pattern. That's kind of weird. I wonder what causes that. Now again, when I introduced this problem, I said there did used to be problems at this hospital with differences in salary by gender. So it depends how long ago that was. Maybe if that was only a couple years ago, then everybody who's been working for a year or more, they were hired when that was still the case. And maybe if they instituted some reforms about a year ago, then everybody hired since then is getting paid pretty fairly. So that might explain why we have this difference here. But already, we haven't even done any formal statistical analyses, but we've got some ideas about things that we will need to do in order to better validate our analysis that is not going to be quantitative analysis. So I mentioned this earlier in the term, this kind of mixed methods that we have to mix qualitative assessments with quantitative assessments. That's really important. And we're seeing that here too. Okay, so we have evaluated, done some exploratory data analysis. We've calculated correlations. We've seen some side-by-side box plots. Now we need to check the normality assumption. So let's check the normality assumption of salary just within each of the different genders. And this is the QQ plot. There's something weird kind of going on here that looks like there's two separate lines for men, but that's not hugely worrisome to me. For women, there does look like there is a little bit of a curve, so I'm not sure what's going on here. So I'm maybe a little bit concerned, but remember the normality assumption is pretty robust, so it has to be a massive violation. So I'm not concerned enough to be able to stop proceeding. Okay, so now let's create a full model, and I'm going to include this interaction term. And in R, my output is going to look like this. So again, this should be familiar from the previous slides that you saw. We have our regression coefficient, the estimates, we have the p-values. And if we take a look at the p-values, it looks like our intercept is significant. Looks like on average, everybody makes about $10. The intercept for men, which is not statistically significant, suggests that the base pay for men is actually about a quarter, 28 cents lower than that base pay for women. But it's not statistically significant. So this maybe needs to be removed from the model. And again, if we were doing a simple ANOVA, even though the group means, the group salary might be different, it's not statistically significant. So then the question is it practically significant? Then I don't know, quarter out of $10, that's, 2.5%. That's something to pay attention to, but I'm not super worried. I'm especially not worried because I know that there used to be a history of men getting paid more than women. This is the opposite. So I'm not really worried that that previous pattern of bias where women were not getting paid as much as men exists, at least from the data as I'm seeing it. Okay, then our next predictor is months. So it looks like for every extra month that our CNAs have worked, their salary, their hourly wage is about 10 cents higher. And that makes sense. The more experience you have, you're going to get paid a little bit more. This is maybe also related to performance. So if you're not doing a very good job, your raises might not be very good. But in general, about 10 cents per month, that means you're getting about, $1.20 raise per year, which is about a 10% raise. That's not so bad on $10. And this is highly significant. The p-value for this regression coefficient is 0.003. So that is quite significant. Then we have our interaction term, which is uh, the interaction between the sex and the number of months worked. And the way that this can be interpreted is the categorical variable here, the indicator variable, was talking about the base rate. So the intercept is kind of like the base rate. So if 10 is the base rate for women, then the categorical variable here, the dummy variable, is there a different base rate for men? Looks like the answer is no, because it's not statistically significant. Then we have our slope. So how much more do people get paid based on their experience? And the answer was about 10 cents. But now it's, do men get bigger raises than women for the same number of experience? And it looks like yes, actually. The p-value is 0.06 and the estimate is about 10 cents. That means for every extra month work, men get approximately a 10-cent higher raise than women. So if a woman's base rate from the data is $10 an hour and she's worked 2 months, this model suggests that her salary would be about $10.20, because an extra 10 cents per each month worked. But the same male would have a base rate of 10 plus 10 cents, plus another 10 cents. So they would be making 10.40. So their raises are twice as high, which is kind of weird. But we also have to keep in mind that this model is also saying that the base rate for men is lower. So if we remove that variable from the model, then maybe it's going to affect the estimates for everything else. So what we need to do is actually recalculate this model. So let's go ahead and do that. I'm going to redo this model, and I'm going to remove the insignificant variable, which was sex. And I'm just going to leave in months and then the interaction of sex time. So this assumes that the base rate for everybody is the same. And when we do this model, where is it? This still included 6 times months. I know what I did. I made a coding error. So this happens often. I apologize for that. Let's try this again. In fact, let's go back and do this model correctly. So I apologize for redoing a little bit of work here, but all the interpretation should be approximately the same. And yes, we still see the same thing. So now let's do the second model, dropping our insignificant term. I'm forgetting a parentheses. And this is including, sorry. I'm making a lot of errors here, but now I think that I have it. Okay. So now we have a model. It says that the average base rate is $9.88. That's highly significant. The number of months, or the increase in salary based on number of months, is actually increased from about 10.8 cents to 11.6 cents per month. It's also more statistically significant. The p-value is lower. And this interaction term is also more significant. It's changed a little bit too, but now it says that the average base rate for everybody is $9.88. For every extra month worked, women get 11.6 cent increase, whereas men get an additional 8 cents increase on top of that. So that's not really good. That's probably bad news. Now we think we have statistical evidence to suggest that there's still some wage differences. And so we need to do some further analysis about this. I'm going to very quickly okay, fix my code. Sorry. So coding errors are a huge problem. You'll see that a lot. Okay. Now I also want to model full. I want to do a stepwise regression. I apologize for sitting here and not talking for a little bit. Coding errors are kind of difficult. I also don't code a ton, but it's important to make sure that you are paying attention that you don't have any errors. So again, I saw something that was weird that signaled to me that I had an error, and that intuitive intuition is what we build with practice. So hopefully you're starting to develop that by doing a lot of examples. You're doing a lot of t-tests. You're creating a lot of confidence intervals. You're doing a lot of normality tests. You're looking at a lot of QQ plots. So slowly you're building intuition, even if you aren't aware of it. So I also wanted to test out the stepwise selection, and we'll start with the full model. The stepwise selection then says to me that we should drop the gender variable. And that's exactly what we did earlier. We saw that that was not significant. We dropped it. We decided to keep the other variables. So the stepwise selection ended up doing the same thing that we actually did. Okay, so let's plot some residual plots. And let's take a look. Okay, so here's our residual versus fitted plot. And what we should be seeing is that the mean is 0 and that there's no pattern. This looks like a pretty clear pattern. It goes down, then goes up again, and then goes down again. So that's not good. We need to do something about this. Let's take a look at the residual QQ plot. The residuals do look normally distributed, so at least there's that. But the residual versus fitted plot did not look very good. Let's take a look at some other plots while we're at it. So this is a scatter plot of our predicted values against our residuals separated by gender. So if we just look at the women, maybe there's a little bit of a curve here, but there's 4 data points here, and then we've got a bunch of data points here. I think that maybe there's some heteroscedasticity. The points are quite spread out, and then all of a sudden right here, there's a good big cluster, and then it kind of gets spread out again. If we look at the males or the men, again, it looks like we only have a few data points over here. If we split this chart in half, the right half for the men look pretty fine. I don't really see a pattern, but for women, I see this possible quadratic pattern here. So I'm not sure quite exactly what's up. I also think we don't have the largest of sample sizes, so I'm hesitant to do anything about it. The plot that concerns me the most, though, is that residual versus predicted plot. And I want to take another look at that. That's this plot. And does this pattern constitute a large enough problem? And after looking at the other residual plots, I don't think I want to do anything about it. So at this point, I would note that this is a potential problem. I would state that I would copy all of the different residual plots I looked at and say, you know what, I think that based on the original scatter plot that we saw earlier on, and let me go back and bring that back up. Okay, here we go. This scatter plot, where we looked at salary against experience and gender, that if we split it by everybody who's been working 10 months or less and everybody who's been working more than 10 months, it looks like there's a really clear separation there. It looks like there's really no difference in salary between men and women. For those who have worked less than 10 months, and for those who have worked more than 10 months, there's a very clear pattern. So if anything, I might even go back and split my data set and then redo all of these steps. Okay. So I hope that you have an example here of how to interpret data sets in R, how we might interpret residual plots, some of the types of thinking that we do. Your homework this week, it prompts you pretty well. So I don't expect you to be able to interpret all of these plots and make decisions the same way that I did. It's highly subjective. So this is probably the most subjective thing that we're going to do this entire term. There's a lot of personal decision-making factors that affect how we interpret each of these plots. So definitely pay attention to the prompts in the questions. You're given all of the information that you need in order to be able to answer the question. If you do have any questions, please reach out. Please let me know. In general, again, multiple linear regression is just an extension of simple linear regression where we have more than one variable. And the key concepts that you should remember is there's an assumption that there is no multicollinearity. So we need the explanatory variables to be dependent. We need our residuals to be distributed normally with equal variance and not have any patterns. So if there are patterns, then we have to do something. Usually that means making a transformation or adding interaction terms in some way, shape, or form. And the way that we interpret our statistical output from statistical software, we tend to look at the p-values for each of the regression coefficients, and we interpret the regression coefficients as the incremental differences or incremental effects on a response variable based on our explanatory variables. So this week is a problem set. Coming up next week is a quiz on chapters 12 through 15. So this is ANOVA. This is correlation and simple linear regression, as well as multiple linear regression from this week. Next week, or the week after that, in week 13, again, that's the week of Thanksgiving. There's no Thanksgiving break, but we do have a problem set. So I do not expect you to spend your Thanksgiving doing statistics homework. I certainly am not going to be spending my Thanksgiving doing statistics, but please do make sure that you plan out your time accordingly that week. And just a quick recap, we talked about the differences between multiple linear regression and simple linear regression, how multiple linear regression is an extension. We quickly did an example of interpreting our R output, doing a multiple linear regression, and we talked about what assignments are due this week. So as always, if you have any questions, please let me know. Otherwise, I will see you next week.